Have you ever watched a river flow or even just water swirling down your kitchen sink and wondered what's really going on in there? It looks simple, right? But just beneath the surface, there's this hidden world of physics, a surprisingly elegant set of rules that governs everything, from the calmest stream to the most powerful flood. Today, we're going to pull back that curtain on the unseen physics of flowing water. So what do they have in common? A massive river carving through a landscape and the water draining from your sink? Well, it turns out they operate under the exact same fundamental principles of fluid dynamics. They're both examples of a very specific kind of flow, one that engineers and scientists study very, very closely. So here's what we're going to cover. First up, we'll define what open channel flow actually is. Then we'll get into water's two surprisingly different speeds. After that, we'll see the dramatic power of something called a hydraulic jump. And finally, we'll look at how engineers use all these rules to build the world around us. Okay, let's dive right in. Part 1. What is open channel flow? And this idea applies to pretty much everything from huge natural rivers all the way down to the simple gutters on the side of the road. Here's the textbook definition. But the key phrase, the only thing you really need to remember, is free surface. All that means is the top of the liquid is touching the air. So think of a river, a canal, even a sewer pipe that isn't completely full. If there's air above the water inside whatever it's flowing through, that's open channel flow. Now, this is a really important distinction. We're probably more used to thinking about the water in our home's plumbing. That's pressurized pipe flow. The pipe is totally full, and pressure is what's pushing the water along. But open channel flow is completely different. It's got that free surface, and it's driven entirely by gravity. The simple slope of the channel is what makes it move.
And that brings us right to part 2, water's two speeds. This is where things get really interesting, because this is where we find the core physics, the real reason why flowing water can be so calm one moment and then so incredibly rapid the next.
You know, the entire personality of that flow, whether it's tranquil and slow or fast and chaotic, can actually be boiled down to a single, unbelievably important number. It's like the secret code to understanding how water behaves.
And that number is called the Froude number. It's really just a simple ratio. It compares the flow velocity, that's v, how fast the water itself is moving, to the wave speed, which is how fast a little ripple can travel across that water's surface. That's it. It's the speed of the water versus the speed of a wave on that water.
Now, to make this idea really click, the source material gives us this perfect analogy, the Mach number for an airplane. We all kind of get that a jet acts completely differently when it's subsonic versus when it's supersonic. Well, the Froude number does the exact same thing for flowing water. So check this out. It's a perfect one-to-one match. For air, if the Mach number is less than 1, we call it subsonic. For water, when the Froude number is less than 1, we call it subcritical. If the Mach number is greater than 1, it's supersonic. And for water, you guessed it, if the Froude number is greater than 1, we call it supercritical. It's the same exact concept, just a different name. So let's break that down. First, if the Froude number is less than 1, we have subcritical flow. Just picture a calm, tranquil, lazy river. The water is moving slower than a wave can travel across its surface. This is why, if you toss a pebble in, the ripples can actually spread out in all directions, even moving upstream against the current. Then you get to the tipping point, a Froude number of exactly 1. This is called critical flow. Here, the water's speed perfectly matches the wave's speed. Any ripple you try to make just seems to hang there, kind of frozen in place, unable to move upstream or down. And finally, if the Froude number pops above 1, you get supercritical flow. Now the water is moving so fast that no wave can possibly fight that current. Any disturbance, any ripple is immediately swept away downstream. This is the chaotic, high-energy world of whitewater rapids. So, what happens when that super fast, supercritical flow suddenly needs to slow down? Well, that brings us to part 3, the incredibly powerful hydraulic jump. This is basically what happens when water slams on the brakes, hard. And incredibly, that supersonic jet analogy just keeps going. A jet creates a sonic boom, a shock wave, to slow down from supersonic speeds.
Well, supercritical water creates its own version of a shock wave to transition back to slow flow, and it's called a hydraulic jump. So visually, a hydraulic jump is this sudden, often really turbulent rise in the water level. The flow goes from being very shallow and fast, that's our supercritical state, and then bam, it abruptly jumps up to become much deeper and slower, which is our subcritical state. It's a dramatic and super rapid transition. And you do not need a giant dam to see this for yourself. You can create a perfect little hydraulic jump right in your own kitchen sink. Seriously. Next time you run the faucet, watch the water hit the bottom. It spreads out in that thin, fast, glassy-looking layer, right? That's supercritical flow. But then, it forms a distinct ring where the water suddenly gets deeper and more turbulent. That ring is a hydraulic jump. So why is this so important to engineers? Because a hydraulic jump is an incredibly effective way to get rid of energy. All that intense mixing and turbulence converts the destructive kinetic energy of fast-moving water into harmless heat. I mean, look at this chart. A strong jump can dissipate up to 85% of the flow's energy, which protects riverbeds and structures downstream from getting torn apart. And this leads us perfectly into our final section, Part 4, Engineering with Water's Rules. Let's see how all these principles are put to work out there in the real world. So when you're designing something like a canal or a drainage ditch, the goal is pretty simple. Move the most water as efficiently as you can. The big enemy here is friction. And to reduce friction, you want to minimize the wetted perimeter. That's just the length of the channel's bottom and sides that the water is actually touching. The most efficient shape of all is a semicircle, but since those can be tough to build, a half hexagon is the best practical shape you can make. Of course, real-world channels are never perfectly smooth. So to calculate the actual flow velocity, engineers use this really famous formula called the Manning equation. Think of it as the master recipe. It takes into account not just the channel's shape and its slope, but also its surface roughness. You know, is it smooth concrete, weedy earth, or a rocky stream bed? And engineers use all kinds of physical structures to control and measure water by basically manipulating its state. A sluice gate, which forces water to flow under it, well, that accelerates the flow into a supercritical state. A weir, on the other hand, which forces water to flow over it, is often used to get the flow right to that critical state, which is perfect for measuring the flow rate really precisely. But getting this science wrong can have absolutely catastrophic consequences. The source material highlights a pretty terrifying fact. The most common reason for bridge failures in the United States isn't traffic overload or anything like that. It's bridge scour. That's when fast-moving water, which accelerates around the bridge's own piers, literally washes away the foundation until the whole structure just collapses. So, from the Froude number to the hydraulic jump, we've seen that flowing water follows a clear, predictable set of rules. And we can use these rules to build dams, design canals, and measure flow. But this leaves us with a final thought. We know the rules. But what happens when, through poor design or just plain neglect, we choose to ignore them? The hidden physics all around us is a powerful force, and it's one that commands our respect and our understanding.